Electrochemistry is the study of generation of electricity from the energy released during spontaneous chemical reactions, and the use of electrical energy to carry out chemical reactions that do not proceed spontaneously. The study of electrochemistry helps us in creating new eco-friendly technologies because the reactions carried out electrochemically are energy efficient and less polluting. A large number of metals, such as sodium and magnesium, compounds like sodium hydroxide, gases like chlorine and fluorine, and many other chemical substances are produced by electrochemical methods. Batteries and fuel cells convert chemical energy into electrical energy and are used on a large scale in various instruments and devices. In human beings, the communication between the cells and the transmission of signals through the cells to the brain and vice versa have electrochemical origins. An electrochemical cell is a device that is capable of either producing an electric current due to chemical action or of producing chemical action due to the passage of electricity. There are two basic types of electrochemical cells. They are voltaic or galvanic cells and electrolytic cells. In voltaic cells, the chemical energy of a spontaneous redox reaction is converted into electrical energy. Voltaic cells are also called galvanic cells. The electrical energy produced by such batteries can be put to useful work, powering our cell phones, radios, and other devices. In electrolytic cells, electrical energy is required to carry out a non-spontaneous chemical reaction. When you recharge your cell phone battery, you are actually running an electrolytic cell. We will be focusing on voltaic cells in this module. There are some key terms that you must first understand before proceeding to study the conductance of electricity. The first key term is electrical resistance, which has been given the symbol R. It is the opposition to the passage of an electric current. Resistance is measured in ohms. The SI base units for ohm are kilograms meters squared per second cubed into amperes squared. The electrical resistance of any object is directly proportional to its length, L, and inversely proportional to its cross-sectional area, A. We need a proportionality constant to turn this proportionality into equality. This proportionality constant is called resistivity or specific resistance and is represented by the Greek letter rho. The SI unit for resistivity is ohm meter. Quite often, its submultiple, ohm centimeter, is also used. Remember that 1 ohm meter is equal to 100 ohm centimeters, or 1 ohm centimeter is equal to 0.01 ohm meters. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then resistance R becomes equal to the resistivity rho. Thus, resistivity is defined as the resistance of a substance when it is 1 meter long and has a cross-sectional area of 1 square meter. Conductance, which has the symbol G, is the inverse of resistance. Thus, we can write that G is equal to 1 upon R. Since R is equal to rho into length upon cross-sectional area, we can say that conductance is equal to area divided by rho into length. The unit for conductance is the Siemens, which has been given the symbol S. Siemens is equal to ohm inverse or mho. The reciprocal of resistivity is known as conductivity. Conductivity is represented by the lowercase Greek letter kappa. Thus, we can write that kappa is equal to 1 upon rho. We can substitute kappa in the equation we wrote a little while ago for conductance. Now we can write that G, conductance, is equal to kappa into cross-sectional area upon length. If the length of the conductor is 1 meter and the area of its cross-section is 1 square meter, then conductance becomes equal to kappa. Thus, conductivity is defined as the conductance of a material when it is 1 meter long and has a cross-sectional area of 1 square meter. The SI unit for conductivity is Siemens per meter. Sometimes this is given as Siemens per centimeter. Note that 1 Siemens per centimeter is equal to 100 Siemens per meter. The magnitude of conductivity varies greatly as shown in the table. It depends primarily on the nature of the material, although temperature and pressure can also affect conductivity. Depending on the magnitude of their conductivity, materials are classified into conductors, insulators, and semiconductors. Conductors are materials with large conductivities, such as metals and metal alloys. Some non-metals, including graphite, carbon black, and some organic polymers, also act as conductors. Insulators are materials with very low conductivity, such as glass and ceramics. Semiconductors have conductivities between conductors and insulators. These important electronic materials include silicon, doped silicon, and gallium arsenide. Apart from the three materials discussed, there are other special types of conductors known as superconductors. Superconductors have zero resistivity or infinite conductivity. The earliest materials identified as superconductors were metals and alloys at low temperatures, below 15 Kelvin. Certain ceramics and mixed oxides show superconductivity at temperatures as high as 150 Kelvin. Now let's discuss about the conductivity in metals, that is, metallic conductance. Metallic conductance, or electronic conductance, is the electrical conductance through metals. As the name indicates, the conductance is due to the flow of electrons in the metal. Metallic conductance depends on the nature and structure of the metal, the number of valence electrons per atom, and the temperature of the sample. Now, let's move on to the conductance in electrolytic solutions. You know that pure water exhibits conductivity, although it is very low. The concentration of hydrogen ions and hydroxyl ions in pure water is 10 to the power of -7 molar. Due to the presence of these ions in very low concentrations, pure water has a very low conductivity. When electrolytes are dissolved in water, ions are released into the solution. As the ions go into the solution, its conductivity increases. The conductance of electricity by ions present in a solution is called electrolytic conductance or ionic conductance. The conductivity of aqueous solutions depends on several factors, including the nature of the electrolyte, the size of the resulting ions, the solvation of the ions, the concentration of the electrolyte, and temperature. Directly measuring the conductivity of ionic solutions is problematic. Passing a direct current into an ionic solution changes the composition of the solution, as electrochemical reactions may occur. Also, unlike a solid conductor, such as a metal wire, we can't connect a solution to a Wheatstone bridge. To measure the conductivity of an ionic solution, we use a conductivity cell, like the one shown in the illustration here. A conductivity cell contains 2 platinum electrodes coated with platinum black, separated by a distance, L, with a cross-sectional area, A. An alternating current source is used as the source of power. The column of the solution separating the 2 electrodes then has a resistance described by the equation R is equal to rho into L upon A. The cell constant, G star, depends on the distance between the electrodes and their cross-sectional areas. G star is equal to L divided by A. The unit of cell constant is per centimeter. If we know the length and the area, we can calculate the cell constant directly. However, direct measurement of the length and area of cross-section of the electrodes are both difficult and unreliable. A better approach is to determine the cell constant by measuring the resistance of the cell when it contains a solution of known conductivity. For this purpose, we use potassium chloride solutions whose conductivity is known accurately at various concentrations and temperatures. The table here shows the conductivity of different concentrations of potassium chloride solution at 298 Kelvin. The cell constant, G star, is equal to resistance into conductivity of the solution. Once we know the cell constant, we can use it to measure the resistance or conductivity of any solution. To measure the conductivity, we can use a Wheatstone bridge. This device contains 2 resistances, labeled R3 and R4, and a variable resistance R1. The conductivity cell is the unknown resistance R2. The Wheatstone bridge is connected to an AC power supply and a suitable detector. When the bridge is balanced, no current flows through the detector. At these conditions, R2 is equal to R1 into R4 divided by R3. Inexpensive conductivity meters are commercially available and can also be used to measure the conductance or resistance of the solution in a cell. Once the cell constant and solution resistance are known, we can calculate the conductivity of the solution by dividing the cell constant by the resistance. The conductivity of different electrolytes in the same solvent and at a given temperature varies. This is because of variations in the charges and sizes of the resulting ions, the ion concentrations, and the ease of ion movement in the presence of a potential gradient. Therefore, we introduce the concept of molar conductivity, which uses the Greek letter lambda with a subscript m as its symbol. Molar conductivity is related to solution conductivity by the equation lambda m is equal to kappa, or conductivity divided by concentration of the solution. If concentration is expressed in moles per cubic meter and conductivity in Siemens per meter, then the unit for molar conductivity can be written as Siemens meter square per mole. To use molarity, which is a far more common concentration unit for chemists, we need to convert the units, resulting in the second equation given here. Let's work through a typical problem together. A conductivity cell is filled with 0.1 m KCl. The resistance of the KCl solution is 200 ohm. The same conductivity cell is filled with 0.03 m NaCl, and the cell resistance is 500 ohm. What is the conductivity and molar conductivity of 0.03 m NaCl? The conductivity of 0.1 m KCl solution is 1.29 Siemens per meter. Note that there are multiple parts to the problem. Here's our strategy. First, we need to find the cell constant, G star. We can do this by using the information given about the KCl solution. We know that G star is equal to conductivity multiplied by resistance. Given that the conductivity of a 0.1 molar potassium chloride solution is 1.29 Siemens per meter. Remember that Siemens is equal to inverse ohms. The resistance of the solution is measured to be 200 ohms. Therefore, the cell constant is the product of 1.29 times 200. The unit of ohms cancels, giving a cell constant of 258 inverse meters or 2.58 inverse centimeters. With the cell constant, we can now find the conductivity of the 0.03 molar sodium chloride solution. We know that conductivity is equal to the cell constant divided by the resistance of the solution, which has been given as 500 ohms. So, we calculate that the conductivity of the 0.03 molar NaCl solution is 0.516 Siemens per meter. We can use the equation shown here to find the molar conductivity from the conductivity and the molarity of the sodium chloride solution. By substituting and evaluating, we determine the molar conductivity to be 1.72 into 10 to the power 4 Siemens meters squared per mole.